when we talk about polarity, we're talking about whether a molecule is polar or not. So we're not talking about ions or not because they have a charge, so we don't have to worry about it. So we're talking about molecules. So we've already decided the bonding within it is going to be covalent. So all of the bonding shown here is a covalent bond. What we're looking at is the molecule and the charge distribution, or how the electrons are arranged around the central atom and overall. So basically I've tried to, not to scale at all, but tried to show that we've got a small electron cloud around each hydrogen, large one around the chlorine, but most importantly I've shown an arrow here, and this is because of the large electronegativity difference between carbon and chlorine, creating a polar bond. So there is actually a polar bond in this. Because it is the only polar bond in this molecule, it creates what's called a permanent dipole in the molecule. So we have a delta minus side or pole to the molecule, and a delta positive side or pole to the molecule. What this means is when it encounters another identical molecule or any other polar molecule, the delta minus side will be attracted to the delta plus side, and that will be a stronger attraction than what we call a temporary dipole, because there will always be delta pluses and delta minuses in these molecules. So they have what's called a permanent dipole. However, if we have a look at something like, let's say, iodine. Iodine's a really good example to show a non-polar molecule. Iodine actually has a really large electron cloud. And because of the size of the electron cloud, even though this is a pure covalent bond, so non-polar, electronegativity difference must be zero because they're the same element, we actually find that iodine is a solid at room temperature, which means there must be either strong bonding between these molecules or a lot of bonding. And what we find is that when we heat iodine, it sublimes. So that gives us a bit of evidence that actually maybe it's not strong bonding, but it's just that there's a lot of bonding. Because of the very large electron cloud, there is a higher probability that those electrons will not be distributed evenly at any moment in time, at any instant in time. So what we find is that iodine often has instantaneous dipoles. These are a subset of the temporary dipoles. So this is a polar molecule. It has a permanent dipole. The relationship between these molecules is what we call a permanent dipole attraction, which takes a long time to write in an exam, I'm sorry, but this is a permanent dipole attraction between these polar molecules. This is much stronger than when we have temporary dipoles, because these dipoles are always there in every molecule. This is a non-polar molecule, so we only have temporary dipoles. So at any instant, you might have a delta minus and a delta plus. Just for a moment, then it can go away, come back again, be flipped, so it comes and goes. If, however, this iodine molecule was to encounter another iodine molecule, a neighbouring one, it can actually induce a dipole, force a dipole on the other one. This is easier if you have a larger electron cloud than it is with a smaller electron cloud. So if it comes next to a neighbouring one, then it can actually, this delta plus side will actually give a small attraction for the electrons this way, which will create a dipole in the neighbouring molecule, an induced dipole, and therefore an attraction can be formed between them. Normally shown as lines like that if we want to. Actually, sorry, I got that wrong. That's a hydrogen bond shown there, which is way too strong for this. Apologies. Just shown as a weak attraction like that. So just some dashed lines. So what we've got here is what we've got here is an instantaneous dipole. It happens just by pure chance. It then induces a dipole in the neighbouring ones. And that's that happens a lot, which means that iodine has a lot of temporary dipole forces, which is why it's a solid at room temperature. This is because of the large electron cloud, meaning there's a higher probability of instantaneous dipoles forming. Okay. However, as soon as I heat it, I tend to break almost all of these because the induced dipoles are uninduced. I don't know if that's a correct word, but they're not induced anymore because the distance between these gets too big. Those instantaneous ones have less of an effect on the neighbouring molecules, so therefore this sublimes, because actually just a little bit of heat increases the distance enough that this induced dipole goes away and the molecules can escape in the gas phase. So, how do we know if something is a polar molecule or a non-polar molecule? Now we know the effect is going to be on things like melting points, boiling points, whether it sublimes or not, that sort of thing. How do we predict it? This is where we're going to need to use the VSEPR theory a little bit. So this is the valence shell electron, valence shell electron pair repulsion theory. So this is where we were doing the Lewis structures, where we were doing the shapes. We bring all that together to see if we've got an even distribution of electrons or an uneven distribution of electrons. So we do need to start with a Lewis structure normally, even if it's a very simplified one. Then once we've got that, we're looking at the central atom. Okay, we're always looking at the central atom and you're trying to see if there are dipoles there or not. Sorry, not dipoles, if there are polar bonds there or not. And if so, we can have a look at the effect. So, this is something that I just sort of think is an easy way to do it. Remember, we're talking about the central atom here. Okay, the first thing to look for is, does it have lone pairs of electrons? Valence shell electron pair repulsion theory. If it has lone pairs, they will repel the bonding ones. For example, if this was a lone pair, it would still push these ones down, so it would have an effect on the shape. If there's a lone pair of electrons, then you will have an uneven distribution. Central atom, not the ones on the outside. Central atom only. So if the answer is yes, then it's polar. It's a polar molecule. It's not polar because it has a lone pair of electrons. It's polar because the lone pair of electrons repels the bonding electrons, which gives an uneven charge distribution. Okay, so there's a bit more to it. That's not the reason that it's polar, but it's a way to identify it as polar. So your other option is no, which means we've got more questions to ask. Okay. Well, my next question then is, does it have polar bonds? And we do this by looking at electronegativity difference. If it's 0.5 or bigger, then the answer is yes. So, polar bonds. So if the answer to this is yes, then we've actually got more questions to ask, believe it or not, because there might be something more happening. So I've got another question to ask here. If the answer is no, however, it's got no lone pairs of electrons and it's got no polar bonds. Good example, CH4, so methane, which is a gas, so very weak bonding between the particles. So if it's a gas, has weak bonding, it must only have temporary dipole forces. This means it's non-polar. Because if it's not got a lone pair of electrons, it must have, according to this theory, it must have a symmetrical three-dimensional shape. And therefore, it must also have symmetry of charge distribution. Because there's no polar bonds to create an uneven pull on the bonding electrons, like in the example given here. So iodine's a good example of this one here, where actually we don't have a central one, so it's not a good one to do, but we don't have a polar bond, so it's non-polar. Okay. If it does have polar bonds, then we have to look at the shape. The shape becomes our key thing. Okay, so that's why we had that lesson on the shapes. So your shape comes into it. And the easiest way to ask this is, do the bonds cancel out? So do those polar bonds, are they antagonistic? Do they pull directly against each other? And you've got to think in 3 dimensions here. So I use the word cancel out, which I don't like. But if you thought of them like vectors, for those who are into physics, if those vectors sum up to 0, it must also be non-polar. For those who hate physics, then just think of it like a tug of war. Okay, if there are ropes on a tug of war pulling, just the polar bonds, not the other ones, the polar bonds were like a tug of war, would there be any movement on that central atom? If it would have moved, that's the negative, the delta minus side. So on this one, we've got a polar bond, non-polar, non-polar, non-polar. Okay, so it does have polar bonds. And this is the direction it would pull because this has got the higher electronegativity. So if I think of it like a tug of war, yep, that would move the carbon this way, the whole thing this way. So this is my delta minus side. Okay, so do they cancel out? And this is in 3 dimensions. So you can look at that as a wee hint. You've got to look in 3 dimensions, which means doing 3-dimensional diagrams. If the answer is yes, sorry, and I've changed colour on this, but I'm trying to get non-polar as red. If the answer is yes, that they do cancel out, then there is an even distribution of charge. So it's non-polar. So you're relying on temporary dipoles again. If the answer is no, they don't cancel out, it means you, like our example, very first example, if the answer is no, then you've got an asymmetry of charge, okay, an uneven charge distribution, then you've got polar, a polar molecule. Okay, any questions on that? It's just a bit of an overview, we'll explore it a bit more in a moment.